So now I'd like to introduce Chris Bruns, who is the Environment and Object Conservation Technician here at Cleveland Museum of Art. He's going to speak to us about materials testing.
Thank you, Jim. Good morning. I'm Chris Bruns, Environment and Object Conservation Technician at ZMA, and an important part of my role here is executing and documenting all of our materials testing. That means I collect samples of all materials that any department within the museum might want to use in contact or close proximity to artwork. Typically, this includes materials for display like showcase construction materials and fabric for covering display blocks and showcase decks. It also often includes materials for storage or conservation of art objects. My work is meant to determine whether or not these materials are safe to use with artwork, because over time, some materials that you might not suspect to be harmful can degrade the materials an institution is working to preserve. For an obvious example, a showcase constructed of wood, let's say oak, will off-gas acetic acid. The acid, now airborne and trapped and concentrated in the microenvironment of the showcase, will have deleterious effects on art objects, degrading organic materials and causing metals to corrode. But other less obvious materials can also contain harmful pollutants. At CMA, we use 3 methods of materials testing that I'll tell you about today. Each has advantages and disadvantages, and I'll cover that a little bit too. There's the Oddy test, which is affordable, low-tech, and effectively tests for every pollutant imaginable. We use a sodium azide test, which is relatively quick to execute, but can be dangerous because of the chemicals used. And the sodium azide test only tests for sulfur. A newer test method for us is the use of acid detection strips from the Rochester Institute of Technology's Image Permanence Institute. AD strips, as they are called, test for exactly what you would imagine and are quick and safe to use, but again, only test for a narrower range of pollutants. It probably goes without saying that an extremely high level of attention to detail is required for any of these tests, because if at any point a sample becomes contaminated, the test results will be useless. So even the relatively quick sodium azide test and AD test strip method require a very clean working environment and very deliberate execution of each step in the test. The Oddy test was developed by British Museum conservation scientist Andrew Oddy in 1973 and has since been adopted by institutions all over the world. The low-cost, low-tech nature of the Oddy test makes it very easily adaptable for different museums' needs. Most museum institutions have their own version of the test, and the CMA uses a version of the test adapted from the Philadelphia Museum of Art's test procedure. So here I am on the home stretch of preparing a batch of Oddy tests last month. Let me explain how I got to this point, because the Oddy test is known for being labor intensive, and I completed a great many steps of test preparation before I got to this point. The Oddy test relies on strips or coupons of 3 types of highly polished metal, being silver, copper, and lead, to detect pollutants emanating from the material sample being tested. The metal should be of at least 99.5% purity. Essentially, the sample material is placed in a microenvironment along with the coupons for a period of time, at the end of which the coupons are evaluated for the presence of corrosion. If corrosion is present on a coupon, it is likely the case that the corrosion was catalyzed by a pollutant in the material sample. Originally, the Oddy test was intended to determine whether materials were off-gassing pollutants, so the material sample was placed in a microenvironment along with, but not in contact with, the metal coupons. The CMA version of the test does place the material sample partially in contact with the coupon, because this mimics how the material will actually be used. That is, suede polyethylenes and other materials are sometimes in direct contact with artwork, so our test needs to account for that. So you can see in this configuration how the metal coupon is partially in contact with the sample when it's in its little pouch, right? This coupon will be in the pouch, half of it, this part not in contact. So the part of the coupon that is not in contact with the sample should only corrode via off-gassing from the sample, while the area in contact mimics more closely how artwork will interact with the sample material and is exposed to higher levels of whatever pollutant the material sample might contain. Once I've collected all the samples, the material samples that will be included in a group of tests, I get to work on preparing the samples for testing. Fabrics are washed individually with no detergent in a washing machine with cold Cleveland City water. Washed fabrics are left to air dry. Each material to be tested will undergo two aspects of the test. There's the accelerated aspect, which takes place in a 1,000 milliliter Pyrex beaker with 50 milliliters of deionized water to raise the relative humidity, and that placed in a scientific oven at 35 degrees Celsius for 4 weeks. The accelerated test includes copper and silver coupons. So in this, you see, these came from the ambient and these the accelerated. The ambient aspect takes place in a 500 milliliter jar with 25 milliliters of deionized water and is kept at room temperature for a length of time that's not predefined, but is at least 4 weeks. The ambient test includes copper, silver, and lead coupons. When the fabric samples are dry after washing, I cut them into strips, and using polyester thread, I sew the strips into pouches to hold individual coupons suspended by polyester thread from a hanging rod made of aluminum foil, and that's what you see on the left there. While the washed fabric samples are drying, I degrease glassware. All of the glassware is degreased first with naphtha, then with ethanol, and lastly with acetone. It's crucial to use borosilicate glassware like Pyrex for Oddy testing because the water used to raise the relative humidity inside the test vessel will leach alkaline material from non-borosilicate glassware and can result in false negative results, inhibiting corrosion from acidic compounds like those found in wood products. I hold off on preparing the metal coupons until the end of test prep because I want them to be as corrosion-free as possible at the start of the test. First, I degrease them with naphtha, reagent-grade ethanol, and acetone, except for the lead coupon, which is degreased with xylene in place of acetone. For the copper and silver coupons, I first use 1 micron alumina until all of the corrosion is removed from the metal. Then I clean polish residue from the coupon using an ultrasonic cleaner with deionized water. I dry the metal with cotton pads, and using a microscope, I very carefully examine all of the surfaces of the metal for any remaining traces of corrosion. If I see any corrosion at all, I repeat the polishing process with 1 micron alumina. Next, I use 0.3 micron alumina to bring the surface of the metal to a mirror-like finish, and again clean polish residue from the metal using the ultrasonic cleaner with deionized water. Finally, I degrease the copper and silver coupons, again with naphtha, ethanol, and acetone. To remove surface corrosion from the lead coupon, I use a fine grit sandpaper, then degrease the metal with naphtha, ethanol, and xylene. When the metals are completely free of corrosion and degreased, I use scissors, painstakingly cleaned and degreased between each usage to avoid contamination, to cut the metals into coupons, each measuring 1 inch by 1/4 of an inch. Each material sample receives a single coupon, and the samples are suspended inside the test vessel. The mouths of the jars and beakers are covered over with 2 layers of aluminum foil. So in the foreground of this slide, you see accelerated and ambient control test vessels. Accelerated and ambient. Each test batch includes a control, which contains everything the material sample tests include, except for the material sample. So the metal coupons are suspended by themselves in their higher RH test vessels. The control establishes a baseline for the amount and type of corrosion I'll be checking for on the other coupons. There should be very little or no corrosion present on the control coupons at the end of the test. 3 types of metal are used as coupons because each has a higher propensity to corrode in the presence of a different pollutant. In this way, the Oddy test can check for the presence of a wide variety of pollutants. The copper coupon detects the presence of chloride, oxide, and sulfur compounds. The silver coupon detects the presence of carbonyl sulfides and reduced sulfur compounds, and the lead coupon detects the presence of organic acids, aldehyde, and acidic gases. The lead coupon is excluded from the accelerated Oddy test because it would likely corrode in the higher temperature environment of the accelerated test vessel, regardless of the presence of pollutants. It wouldn't be likely to provide any useful information. Our scientific oven can hold a maximum of 18 1,000 milliliter beakers, so that is the limit for the number of Oddy tests I can run simultaneously. Because it's more efficient for me to run more tests at once, I try to make sure I get as close to 18 as possible. From start to finish, I expect Oddy test prep for 18 different materials to take approximately 1 week of fully dedicated work. So in case this isn't totally obvious, these are the coupons at the end of an Oddy test, and These are the samples. There's no sample in the middle image. After 4 weeks, I remove the accelerated Oddy tests from the oven and open up the accelerated and ambient Oddy tests. Sometimes, as in the photos shown here, the results are very obvious. In the tests above, a great deal of corrosion was created on each coupon. In cases where the corrosion is less obvious, I use a microscope to examine the coupons. Depending on the amount of corrosion present on a coupon, the material sample can be deemed acceptable for permanent use with artwork, or acceptable for a one-time use, not to be used in direct contact with artwork, and only for the length of a temporary exhibition, or not to be used, deemed unfit for use with artwork. After being assessed, the ambient and accelerated tests are photographed together by Joan Neubecker, our department conservation photographer, to document the results and to make it easier and more useful to share our results via the AIC Wiki, which I'll tell you more about in a few minutes. At this point in the Oddy test, the accelerated version is finished. If the accelerated portion of the test passed, the ambient test can be reloaded into its Pyrex jar and continued for any length of time, and the tester can check back periodically to see if and how corrosion is developing on the coupons. Obviously, if the accelerated portion of the test failed, there is no need to allow the ambient test to continue to run. The Oddy test has several drawbacks to note. One major objection with the Oddy test is that it does not determine what the pollutant is. A positive test result only indicates that something caused the metal coupon to corrode, but from there's no way to know specifically what the pollutant could be. Another issue with the Oddy test is that it is very easy to generate a false positive result, because contamination can happen at any point during test preparation, and there's no clear way to tell if or when contamination may have happened. And the Oddy test is also by nature subjective. There's no real method for measuring the exact amount and type of corrosion present on a metal coupon at the end of a test, so it can be difficult to keep the test consistent. An alternative to the Oddy test that we have relatively recently adopted at CMA is the sodium azide test. The sodium azide test, which tests only for sulfur, is a much faster test to perform than the Oddy test, but has also much more pronounced risks for health and safety. Sodium azide is the chemical used to inflate automobile airbags, and it's extremely volatile and poisonous. In the presence of sulfur, sodium azide produces huge amounts of nitrogen gas, which is what inflates a car's airbag. But by the same principle, a sodium azide solution can test for the presence of sulfur in materials under consideration for use with artwork. The idea is to perform the test on a very small scale. Of course, it is necessary to use every precaution, including wearing goggles, a respirator, gloves, apron, long sleeves, to carry out the work inside a fume hood and to dispose of all materials safely. The sodium azide test is probably not for everybody, so unless you are confident that you can carry it out safely, it is probably best not to try it. As a side note, sodium azide is light sensitive, so it's important to store it out of the light. What you're looking at in this slide is a photomicrograph of a sodium azide test that is showing a reaction, meaning there is sulfur present in the fabric sample being tested. There are numerous nitrogen bubbles being formed quickly. The test procedure is fairly straightforward. After you've created your sodium azide solution, which includes sodium azide, ethanol, and potassium iodide, a material sample is placed on a glass microscope slide with a glass cover on top. Using a dropper, you place a drop or two of sodium azide solution at the corner of the slide cover. As the solution wicks in and is absorbed by the material sample, the reaction is observed through the microscope. If bubbles form within 2 minutes, the sample can be deemed unsafe for use with artwork. As with the Oddy test, the sodium azide test evaluates materials and places them into one of 3 groups: acceptable for permanent use, acceptable for temporary use, not in contact with artwork, and unacceptable for use with artwork. The distinction is found in how vigorous a reaction occurs. More bubbles that are larger and produce more quickly indicate a larger amount of sulfur present in a sample material. As the sodium azide test tests only for the presence of sulfur in a material, it is not adequate to deem a material safe for use with artwork. Effectively, it can weed out materials and allow me to skip performing an Oddy test on them. If a material fails the sodium azide test, it should also fail the Oddy test. If I can avoid having to go through a labor-intensive Oddy test, I can save a lot of time and museum resources. Acid detection strips from the Rochester Institute of Technology's Image Permanence Institute provide an easy way to check for acidity in storage or display areas. The strips, which contain light-sensitive dye bromocresol green sodium salt, will react with acidic vapors and change from blue to green and then yellow in the presence of acidic vapor. A microenvironment can be created using, say, a sealable polyethylene bag, and the material sample and an AD strip can be placed inside. If, over the course of several days, the color of the strip begins to yellow, it indicates that the material sample is off-gassing acidic vapors. Of course, even if the color of the AD strip does not change, the material sample should still undergo the Oddy test. AD strips can be seen as another method to relatively quickly and inexpensively weed out materials that would fail the Oddy test. This slide shows a set of AD strips that were used to evaluate possible display conditions. These strips help determine how some aspects of showcases needed to change to mitigate off-gassing of acidic vapors. So now I'm going to talk a little bit about pollutant mitigation techniques. Especially in a city like Cleveland, airborne pollutants are a fact of daily life. To mitigate pollutants in a microenvironment like a typical museum showcase, there are two main methods we use. We use activated charcoal, which is made from coconut shells in all of our showcases. Activated charcoal, which is basically the same thing used in a Brita water filter, has a tremendous amount of surface area, and the carbon naturally wants to chemically bond with pollutants. So when gaseous pollutants pass over the activated charcoal, they become trapped. And more specifically, to prevent metals from corroding inside a showcase, we have begun using corrosion intercept foam and the associated display case filtration system. It's a battery-operated device that uses a fan to push air over a small disc of corrosion intercept foam that you see attached to the device here. The foam functions as a kind of sacrificial purification system, not unlike silver cloth. Instead of a pollutant causing an art object to corrode, the pollutant causes metals in the foam to corrode. The battery and the foam should last about 3 months of continuous operation. And now, I'd like to share with you how we share our materials testing results. After our completed Oddy tests are photographed, results are uploaded to the AIC Wiki, which you are all invited to check out and participate in. If you go to that website, this website, you can get involved. I will now click through several slides showing there is where you click to get to the wiki. You can get information on materials testing at a more general level here, and then you can click through to data tables, and you can search for Oddy tests by type of material, where you'll find out who did the test, when it was done, and what the results were. And this will be available, I think, to everybody after the presentation, so in case you didn't copy all of that down, you will not have lost it. Here's some information on where we buy our supplies for materials testing, in case you were curious. And finally, a bit of very basic further reading on the genesis of materials testing. Thank you.